Okay, I think we shall start. At this moment, we lost our. Yeah, thank you for organizers for helping us to have this online session. And I will ask you to turn off the microphones when you're not talking. Welcome to the first Ukrainian NLP workshop at the ICTERI conference 2021. My name is Alexey Molchanovsky. I'm co-chair of this workshop, and I want to introduce my co-chair colleagues, Alexey Ignatenko from Institute of Software Systems, Kyiv, and Andrei Glebovets from National University Kyiv-Mogila Academy. It is our pleasure to have this workshop today's morning, and a couple of words why we actually initiated this this kind of event. So none of us, me, Alexey, and Andrei, are not working deeply in Ukrainian natural language processing, or probably even not really deeply in NLP at all. But we understand that it's one of the crucial domain for development for artificial intelligence in Ukraine, because as I repeatedly saying that nobody will create Ukrainian NLP instead of Ukrainians. So this is a rather good motivation for me and for my colleagues to initiate this kind of workshop. So we are happy to have you, dear colleagues, here. We had roughly 15 submitted papers, and among of them we picked 5, and which will be presented today. They are from different perspective of working with Ukrainian NLP. Those are different tasks related to the natural language processing, but all of them are combined under same umbrella of Ukrainian language. And we are happy to have you to present your results at this workshop. Also, we will have a keynote speaker, John Mccrae, who will give a talk on how on their project Cardamom, dealing with under-resourced and low-resourced languages, because despite of all, Ukrainian language is still could be treated as low-resourced in terms of natural language processing. So please stay with us for the next 3 or 4 hours. And let us jump into our main program. And I want to pass my word to Alexey Ignatenko, who will lead the first half of our workshop. So Alexey, please, the mic is yours.
Thank you, Alexey. And I want to announce first presentation today. It's Yulia Makohon and Igor Samohin, targeted sentiment analysis for Ukrainian and Russian news articles. Please, can you share your presentation?
Good morning.
So you have approximately 20 minutes for presentation, and 10 minutes we plan for discussion and questions. Please.
Good morning. Is everything okay with the presentation?
Yeah, but you can.
I'm sorry.
Yeah, go to present mode. So yeah.
I see. Okay.
Yeah, it's excellent. Thank you.
Well, I'm sorry for the small delay. Well, it will be convenient to have the presenter meeting view. Maybe I can have 1 minute. I did it in.
Okay. Take your time.
I cannot understand why it's doesn't work the way that I tried. Well, and so thank you. So my name is Yulia Makuhon, and this is our work with Igor Samohin called Targeted Sentiment Analysis for Ukrainian and Russian news articles. This presentation is about the work we did together with Igor in Semantrum company during 2018 and 2019. Semantrum is a big data product with a focus on PR effectiveness measurement. It's very important for our clients to find a positive and negative mentions of their monitored objects in Ukrainian and Russian news. The objects are usually organizations or people. So our task was to advance the sentiment detection algorithm the company had. So we created a data set with clear annotation guidelines and trained a transformer-based model on it, and it worked. What do we plan to discuss today? The topics fall apart into two logical sections, one about defining the task and annotating the corpus, and the other one about data preprocessing, training, and model selection. So let's start from the task definition and annotation. And what makes news special for sentiment annotation? The goal of sentiment analysis is to computationally identify opinion, emotion, and attitude in the text. It could be done on the document level, on the sentence level, or as in our case, towards a given target. The task to identify sentiment polarity towards different aspects of the entity is called aspect-based sentiment analysis. The first thing we did at the start of the research was looking for existing corpora on targeted sentiment in the news. But to our disappointment, at that moment, there were no suitable datasets for targeted sentiment analysis in our domain. For Ukrainian and Russian, the work was mostly about the rule-based and lexicon-based approach in other domains or on document-level sentiment. Even more, the field of targeted sentiment analysis was under-researched. The main work was concentrated on Twitter and on user reviews. Those texts, stylistically and lexically, are very different from the news articles. The sentiment opinion in the news is rarely expressed explicitly, but often the exposure of facts is to form the reader's opinion about the topic. So our choice was to start the dataset annotation to get data for training and evaluation. Preparing this paper now in 2021, we found that this main UTSC dataset was introduced by Hamburg and others. It could be compared to ours with the Mcrae F1 about 59%. You can see the SOTA F1 on user reviews for the task of aspect-based sentiment detection are here to the left, and the numbers are significantly higher. Among other things, it demonstrates that the news domain is harder to analyze. And what about the intuition about news annotating for sentiment? When people think about news articles, it's natural to start with the question, is it good or bad news? Some document-level sentiment corpora were annotated this way, bringing the main focus to the reader's perspective. Let's try it. If we ask, our team won the competition, is it good news? Yes, we mark it as a positive sentiment polarity. If we ask, the pandemic continues, is it good or bad news? We say, yes, it's bad news, and we mark it with negative sentiment polarity. But our task is to find out opinion polarity about some entity in the text. In many cases, it seems that asking, is it good or bad for the entity works. Trying again, John won the election. Is it good news for the target? Yes, seems it should be marked as a positive sentiment polarity towards John. And what about John lost the election? Is it bad news for the target? Yes, maybe works, but maybe not in some cases. In many cases, it could be confusing. Our clients used to think about positive and negative mentions. Sorry about for the sad example about John, but it's a corner case that reveals many possible pitfalls. Obviously, it's bad for John to be dead. However, it doesn't look like a negative mention for John. Isn't it good to be a doctor? But to be a politician? Is it good enough to become the vice president? People consider different things good and bad, especially when it comes to political views or, as we can see now, the health issues and vaccination. It would be useful to have one question to describe our task and formulate the problem. But it seems that this one, is it good or bad for the target, leads to subjectivity in annotation. And we also should take into consideration that many texts require background knowledge of the situation to understand right and wrong, and some of the texts are just fake news. It took us some time and research to formulate the right question for our needs. It came out to be the question not about the entity, but about the text statement. How could the text affect public opinion about the entity? But that's a rather hard question for annotators. It requires a lot of clarification to be used as annotation instruction. So we needed to transform it to some simpler annotation steps. With some modifications, we adopted the approach proposed by Dr. Saif Muhammad in this paper. An annotator should assess only the language, not the views, and ignore possible disagreement with the speaker. The single annotation task is to work with the whole document. An annotator is supposed to label all the pre-selected entities in the document. The entity could be a person, an organization, a product, some event or piece of art, but not the location. To give annotators an algorithm for each entity, we split annotation into 3 steps. The first question is the target a speaker? The question tackles the problem of finding the opinion target and helps to mark doublessly neutral entities, because speakers in most cases are neutral. The second step requires looking for the emotional phrases about the entity. After that, an annotator is supposed to evaluate if facts in the contexts could be considered a success or a failure. All the questions are treated separately. Let's try it. We should mention that the real document often is hard to decide what context in the real document often it's hard to decide what context is relevant to the entity. In the simple text on the screen, the first mention of Harry has a context of 2 sentences, and the second has a context of 1 sentence. So in our guidelines, we gave some constraints, but it was up to the annotator to choose the context to analyze. And also, we see the example when John is a speaker and says something about Harry. And this should be marked as neutral, as in many cases when someone is a speaker. We encourage annotators to justify their decision based on the presence of relevant phrases in the text, the so-called lexical marks. If definitely there are more positive lexical marks than negative ones, the entity should be labeled as positive, and vice versa. Neutrality means the absence of both positive and negative phrases about the entity. Entities are marked with a certain label if there is no way to choose what marks are more important. The most common cases are ironic or sarcastic statements. So we can see that John has died is a neutral mention because there is no positive and there is no negative mark. But if we add the great Dr. John has died, it's a positive mention of John. And then we have 2 important examples. If we say that abominable John has died, the text has lexical marks of negative emotions. And in the sentence, Dr. John failed to help the patient, it contains the negative fact about the target. We provided independent guidelines on detecting the lexical marks for emotion and fact, but in many cases, the same phrases could be considered as marks both for emotion and for the fact, intensifying the sentiment. For annotation, we selected 1,000 Ukrainian and 1,000 Russian news articles. It was required to check if there are any suitable entities in the text with non-neutral contexts around. There was also a problem finding positive documents, because most non-neutral news is negative. For this purpose, we used text not only about politics, but from different topics like health, sport, and technology. Our annotation design required pre-selected entities. As a first stage, we asked annotators to annotate the texts selected for sentiment annotation by almost standard named entity recognition rules. The entities were used as sentiment annotation targets, but also to train NER models for Ukrainian and Russian. We asked 3 annotators to label the entities in the text. One of the annotators was chosen then to do super annotation and to make a final decision about conflicted entities. As a metric of disagreement, we used the average number of choices per entity. The numbers you can see on the slide mean that about 1 out of 10 entities needed the super annotation. Also, it serves as a quantitative proof that this task is rather hard for humans. It definitely is, because it requires concentration and deep text comprehension. Anyway, in a few months, the annotation had been finished and the annotation guidelines show themselves as reasonable. Sometimes annotators were not sure if the entities should be marked as neutral, but rarely confused negative and positive samples. However, some superannotator work was required due to mistakenly labeled sentiment type, factor emotion. And then we could proceed to preprocessing and model selection. And the first thing to do as a preprocessing appeared to merge emotion and fact. First of all, because of the insufficient number of emotional context in the news. It was easy to do it in an ambiguous way, though, but entities labeled uncertain were excluded from the training and testing. There were rather few of them, less than 100. We also excluded some documents and ended up with 1,958 news articles in total. And you see the number of entities. I'm sorry. The number of entities. It's not a big corpus, and only about 15% of entities were marked as non-neutral. And look, it's important that you see that statistics both for Ukrainian and Russian, and not from the beginning, but we made a choice to combine Ukrainian and Russian text into one data set. It made sense due to the availability of multilingual transformers and allowed us to have more data for training. And it was important to decide what text window around the entity to use for the model. The choices were to use a single sentence, a few sentences, or to ignore sentence boundaries and work with a token window. The last option showed itself as the more robust one, so we stuck to it. And the span of 20 words to the left from the target and 20 words to the right is sufficient in most cases. As a baseline, we used a simple feed-forward neural network. And as you can see, this approach wasn't really suitable for our needs, with F1 macro around only 42%, but mostly because of the low scores for minor but most important classes. More advanced neural network architectures didn't help too, as the model lacked background knowledge and failed to generalize. And that's why the massive pre-trained multilingual BERT model introduced in 2018 was a natural place to look for improvement. And here we want to present the experiment results for fine-tuning the multilingual BERT model and additionally for RuBERT model. RuBERT is based on multilingual BERT, so it retains tokens and bytes from Ukrainian texts. At the same time, it could improve performance on Russian texts, and it makes it interesting to try. We also tried distal BERT, but with distal BERT, the model quality is decreased by about 2 or 3%, so we decided not to proceed with experiments. And larger transformers like Roberta look promising, but we have a production environment with limited resources, so we considered not to use it. And we trained models for 3 epochs, like it usually do, and BERT uses word piece as a tokenizer, dividing words into subtokens. So our hyperparameters are token window size, in words and word piece window size in subtokens. Hyperparameters were chosen so that most texts in the sample are not truncated and used in full. The pattern was used for the contexts on the document start and in the end. And we can see that both models perform significantly better than the baseline feed-forward network, and the differences between them are not really significant. We also see that F1 for the positive class is usually worse than for the negative class, as to be expected for the class with the fewest examples for training. So the numbers are about 67% for F1 macro, about 50% or a little bit more for positive class, and about 56% or 55% for the negative class. And those numbers are far from 100%. On real data, the model works well. The most important for us is that it doesn't confuse positive and negative examples and is confident in the context where humans are also confident. The model received positive feedback from the customers and company analytics. It still somewhat lacks irony comprehension and needs additional training on social networks because of the different lexicon. We selected multilingual BERT for the production environment. Results with RuBERT show the possibility of further experiments on pre-training, not just fine-tuning transformer models. We suggest that our annotation design resulted in high-quality data set for the hard task of targeted sentiment analysis in the news. We couldn't exploit the division of sentiment on fact and emotion because emotional words are rarely used in the news. Though this decision led to more work for annotators, it also allowed writing more clear annotation instructions. And what about the future work? The plans for future work include experiments on better neural network architecture on the dataset. It's still possible. And also we plan to enhance the research scope to social networks in Ukrainian and Russian. And that's all. Thanks for your attention.
Thank you, Yulia, for interesting presentation. Thank you for meeting the time schedule. It's very appreciated. We have some question, I believe. Do you have any questions, please? Yes, Alexei.
Thank you, Alexei, and thank you, Yulia, for interesting presentation. So a couple of more rather technical questions. So what was the configuration of your machines to train these networks?
Not some. Maybe Igor can answer more clear, but I don't remember something really special there, like about 64 maybe or 32. How much?
Hello. We did have GPUs with about, I think, 12 gigabytes of memory.
Even 12, yes?
Yes, it's about like not the newest generation of GPUs, and this work was done is 2018, 2019, and it was like on GPUs made in 2017, I think.
Okay, I see. So this question was about the number of epochs. So you, as far as I understand, you trained for 3 epochs every model, and so is it enough? I mean, like why 3?
Yeah,
why
actually, in transformers, in fine tuning, not in pre-training, 3 epochs, maybe 4, maximum 5 is like you can see it in other papers. It's a common number, and usually 3 is enough. And yes, of course, we tried to train for more, but it didn't improve results much or at all. So 3 or 4 epochs usually enough for fine tuning.
Okay, yeah, interesting. Thank you. And another question regarding the data set. So you had a great job for acquiring the data, and does your data set available anywhere online?
Oh, no, sorry. It's a proprietary data set, but well, I think it's possible to discuss some collaboration with the company management. So I don't know. It could be done in some cases.
I think we should, in preparation of next workshop, explicitly mention that works with published dataset are encouraged or something. Do you have any other questions? Andy? Yes.
Okay, thank you very much for your presentation. I have one question for you. What was the main idea to organize in such way your data set with Russian and Ukrainian language? What was the benefits from this organizing, not only to increase the number, what was other incomes?
Well, we thought that it could benefit from the common subword tokens. Possibly it works, but we are not sure really, because well, the main reason it worked may be because as I said, of the data set size increasing, and also without multilingual models, it couldn't be possible.
Yeah, I would like to continue. Of course, first, we tried to separate these data sets into like different models, but for BERT, especially for multilingual BERT, which contains subword tokens for both Ukrainian and Russian languages, it was possible to train a common model, which was not worse than the separate models. And it allows us to like economize on resources, because one model in production is like consumes 2 times less resources than 2 models in production. So if we have the same quality for like less resources, it was like a natural choice.
Thank you, Igor. It really was an important
you.
remark. And
Thank
also
you.
it allows...
Alexei, you have another question? Thank you.
Yes.
Yeah, I'd like to elaborate on the Andrei's question. So you have this two main models you play with, this MBERT and the RuBERT. So as far as I understand, the RuBERT was already pre-trained for Russian language. And when fine-tuning the RuBERT model, you used only Ukrainian sentences, Ukrainian part of your data set, or both?
No, see, RuBERT was based on BERT multilingual, so it was using as an initial weights from BERT multilingual. Then it was pre-trained further on Russian text, so it works better for Russian. But it was fine-tuned on both Ukrainian and Russian text, because it was like unsupervised pre-training on Russian Wikipedia, but it was not suitable for Russian sentiment analysis. So it was required for us to fine-tune it further on Russian sentences. So of course it was fine-tuned later on both Russian and Ukrainian sentences.
And so may you switch back to the results table, Yulia?
Yes, of course.
So I'm curious whether this difference between RuBERT and MBERT was significant.
No, it was not significant, and I think we tried to show this. It was the main difference is in optimal hyperparameters such as token window size and the length of sequence, but it was mostly because RuBERT has more granular, bigger vocabulary for Russian language, and it's subword vocabulary, so many of these subword tokens are the same for Ukrainian language. So because of this, smaller size of sequence is enough for RuBERT because of more granular subword tokens.
And also, how do you think if, for instance, we will try to create some kind of RuBERT, but specifically for Ukrainian language, pre-trained based on Ukrainian Wikipedia, let's say, Does it will it improve the results? How do you think?
Well, we should try. It's possible.
We should try. It's probable, but we see here that like possible improvement in this architecture, in this setup, is probably won't be more than like, I don't think it will be more than 70%, more than 0.7. So I think something more is needed than just another BERT. I think we can maybe try with other transformer architectures. Like we didn't do it here, but I think it is possible for the future.
Okay, and regarding the size of data sets, so how do you estimate the quantity of the data set? Is it enough? So as far as I understand, there are about 40K sentences or entities at all.
It was definitely not enough for feed-forward network. And it was also not enough for some RNN or something like this. And these experiments we even didn't include into the article. So because the main reason we switched to transformer because of the background knowledge of the bytes the transformer has. Because these contexts are maybe rare, even for this data set. One example is not enough to generalize well than to the real data. You see what I mean? That then we had nice maybe results on test, but not that good as with transformers. But on real data, they were not suitable at all.
Probably a last question from my side. So how much time you spent for gathering this data set?
Gathering, well, we have a lot of data. We have a lot of data, so gathering was not a problem. The problem was to select the data for annotation.
OC means annotation performance.
For annotation. Yes, we used the rule-based or some other kinds of document level sentiment algorithms to find the pieces that could be of interest to us, and that required some time. But about some annotation, it took maybe a few months, I think.
Well, probably 3 or 4 months.
And maybe yes, more. Maybe because it's hard to say now. It was a long time ago. But yes, it's really a hard job for annotators, and we tried it too.
Yes, it's a bottleneck for scaling for this approach. Yeah, thank you so much.
The problem is when you try to teach the annotators the approach, and then they work faster.
Okay, last maybe question from my side. Is it possible for you to estimate the cost of annotating of this data set, the cost of this project? I mean, without any details, just approximate cost. Can you tell it?
I cannot really say, but possibly maybe about 50,000 hryvnias, maybe something like this. I don't know how to make annotate. Yes, annotate.
Okay, thank you for
maybe more
presentation. Okay, I've heard the estimate, the number. Okay, thank you for your presentation. And let's we have small delay, but I think we will catch up. So our next presentation, the Dmitry Klyushin and Yulia Nikiforets, non-parametric methods of authorship attribution in Ukraine. Please present your work.
Good morning. I would like to present you my work with Dmitry Klyushin. Is everything okay with the presentation?
Alexey, we cannot hear you. You're muted.
Sorry, I mean you were on 9th slide. You need to go to first one.
I'm sorry, you don't hear me?
No, we hear you, but we don't see your. Yeah, now
Yes.
it's fine.
So let's start. First, I will tell you something about the structure of my presentation. First of all, it will be the formulation of the problem, then some short literature review. Then we will talk about theories we used to solve the problem, and then we will talk about experiments and their results. First of all, formulation of problem. We compared two non-parametric methods of authorship identification of Ukrainian literature texts based on Occlusion Petunian test and its simplified version. The method of n-gram selection is applied. For testing, we chose 200,000 characters from 10 Ukrainian authors, and the statistical hypothesis that the text belongs to a certain text corpus is tested. Short literature review. The use of letter combinations n-grams is a stylistic feature for recognition by the author, was first suggested by Kiel. In future, this direction was developed by many other scientists. In this work, different approaches to automatic identification of authorship were considered, and experiments were carried out to assess the accuracy and effectiveness of the proposed methods for attribution of literary text written in a different language. The Kiel's idea was to compute the relative frequencies of letter pairs within text samples and compare them using a neural network classifier. Stramatis considered computational issues of the authorship identification and discussed methodologies and criteria for authorship attribution. Orlov and his co-authors proposed a statistical test for classification of literature texts using an information about distribution function. Orlov investigated distributions of distances between distributions of trigrams, estimated the accuracy of the classification using the frequencies of combinations of letters depending on the length of the text, and estimated the specificity and sensitivity of the proposed method. Orlov's approach was further developed by Durnev, Pente, and Pugachi papers. Occlusion proposed an original rigorous statistical test for authorship detection using estimations of homogeneity of distributions of n-grams, monograms, bigrams, and trigrams in text of literature text in English and Russian literature. This method is based on Occlusion Petunian test. So let's move on to solving the problem. First of all, I would like to meet you with the Hill-Dempster assumption on which the method is based. According to assumption, we have an if exchangeable random values x1, xn, following an absolutely continuous distribution, and the probability an, it is the probability that xn plus 1 will be in the following interval, where xn plus 1 follows the same distribution and xi and xj is i's and j's order statistics. Let samples x and y be drawn from distributions f1 and f2, and let the event AIJ case will be that y will be more than xi and less than xj. Then we have hash ij's, it's the amount of ij divided by the size of sample y m. Oh, I'm sorry. Then we will consider Wilson confidence interval for the probability of A by the following formulas. We calculated the lower and the upper bounds for the Wilson confidence intervals. They depend on the parameter z. We choose z equal to 3. The significance, then the significance level of the interval will be less than 5,000. Put n and l the following values, and then we can find rho. Which is the probability that x and y and y are drawn from the same population. We would name it P statistics. Since the P statistics is a binomial proportion, constructing the Wilson confidence interval for the P statistic, we can formulate the following decision rule. If P second is greater than 0.95, then the null hypothesis is accepted, else it's rejected. And now we will talk about a simplified version of the Occlusion-Petunian test. We will select m times random numbers I and j, such that j will be greater than I and less than n, and do the previous procedure only for less amount of intervals. The decision rule will be the same as in previous method. It's easy to see that in the original version of the Occlusion-Petunian test, we must exhaust all pairs of x. Therefore, the algorithmic complexity of the text is the quadratic order of growth. But if we use only m random intervals, where m is more than 100, but much less than in previous test, the algorithmic complexity may be reduced to linear order, because of the well-known fact that the relative frequency of Bernoulli chains is stabilized rather quickly. In our experiments, we used 100 trials according to practical recommendations. Let's move on to the experiments. Testing was carried out on a set of 10 Ukrainian authors. 200,000 first characters of the text were used, each of which was divided into k parts, from which samples of the corresponding sites were selected to determine frequencies of n-grams. The accuracy of the author's identification depends on the number of fragments into which the text is divided. So for each type of n-grams was chosen its own k. Now you can see the simplified P statistics for monograms and their confidence limits. In another 2 slides will be the same data but only for b-grams and trigrams. The homogeneity measure of n-grams in text of 10 selected Ukrainian authors varies very slightly for monograms, b-grams, and trigrams. It attains a maximum when we compare text of the same author and allows clearly different the text of different authors. However, the homogeneity measure has a very narrow range, and the maximum of per statistic for bigrams is slightly expressed than for monograms. And in case of trigrams, the p statistics becomes a constant. Obviously, this effect may be explained by the fact that for clear detection of homogeneity of bigrams and trigrams distributions, we must analyze more long text. Note that the homogeneity measure between text of the same author is greater than between text of different authors. It's interesting that the maximum of the graph of the homogeneity measure corresponds to the comparison between the text of the same author and is the most clear for monograms, less clear for bigrams, and almost invisible for trigrams. Next part of my talk will be results. After considering confidence limits and the values of statistic for the statistic for the per statistics and simplified per statistics, it was easy to see that the p statistics and the simplified p statistics are varying in narrow range. All p statistics are almost constant for all writers. The variations are decreasing in the sequence of monograms, bigrams, and trigrams. To identify the authorship with statistical significance, we cannot rely only on features, but must analyze the confidence intervals for homogeneity measure and use the following decision rule. If upper confidence bound for homogeneity is greater than 0.95, then the texts are considered as written by the same author. If the upper confidence bound is less than 0.25, then we consider that the texts were written by different authors. Its result for monograms, K was equal 30 and significant level 0.05. The sensitivity for per statistics is 100%, but specificity is equal only to 17%. If we will talk about simplified per statistics, the sensitivity and specificity are equal to 100%. It means that we correctly identify the text of the same author and distinguish them from the texts of other authors. For bigrams, results are quite some different. The confidence intervals are narrower comparing with the confidence intervals for monograms and don't contain 0.25 in all the cases. In per statistic, the sensitivity is 100%, but the specificity is equal to 0. It means that all the texts are considered as different. It's interesting that increasing the significance level up to 0.1 instead of 0.05 makes this test an ideal one since its sensitivity and specificity becomes equal to 100%. In simplified per statistics, sensitivity and specificity are equal to 100%. It means that we correctly identify the text of the same author and distinguish them from the text of different authors. Results for trigrams. In case of per statistics, all the texts are considered as different. The confidence intervals are narrower comparing with bigrams and monograms and don't contain 0.25 at all. As in previous case, increasing the significance level up to 0.1 also makes our test ideal, and its sensitivity and specificity becomes equal to 100%. In case of simplified statistics, all the texts are considered as the texts of the same author. In conclusion, I would like to say that both variants of statistics used to identify authorship of a text provide high accuracy when the volume of the text isn't less than 200,000 characters and the significance level is 0.1. The simplified statistic gives the best results for monograms, for bigrams, and trigrams. Original and simplified statistics give same results. In case of large size of n-grams, the text should be broken into a smaller number of fragments. The use of the modified statistics provides high accuracy and at the same time significantly reduces the time spent. That's why the most clear results are obtained for monograms, less clear for bigrams, and in case of trigrams, the statistics is a constant and doesn't allow detecting the authorship. It's the end of my presentation. Thank you for attention, and we can move on to your questions.
Okay, thank you. Let me then ask first question because it's about the idea. So did I get it right that you take different texts by different authors, then divide to the monogram, so it's containing one character? Monogram is only one character.
Yes.
And you divide them for letters, this text, and then you try to recognize what text was written by what author. But the monograms would be the same. It's the same alphabet. I mean, what's the difference?
We chose one text from authors and divided it into K parts. In example of monograms, it was 13. Then in this part, we calculated the amount of each letter and had a sample. The size of its sample was 8 because we divided our text into 8 parts. For example, in first part, the amount of letter K of letter M was 10. In second part, it was 9, and so on till 8. So we have 8 numbers.
Now I understand. Okay, Alexei, please, you have a question.
Thank you. But is it correct to say that monograms are in the base of words, not characters? So, so when you split on the monograms, you split the text based on words. And when we say, for instance, bigrams, it's the chunks with 2 words, and trigrams, chunks of 3 words.
I think I don't understand your question. We chose 1 character, 2 characters, and 3 characters. It was combinations of letters, but not words. Okay, it's interesting. So, and my question here is about more of the size. You mentioned this number of 200,000 characters. The first 200,000 characters you take from the text and then have this processing. So why this number? Did you try to use a smaller number? So my question probably here is, what is the minimum number of characters you need to process to have the significant result of picking the right author? Choosing the number of characters, we think about previous works in which there was used the same one, but as you can see, for monograms and bigrams, it's quite okay to use 200,000 characters. But when the number of n-grams becomes bigger, you should choose longer text. And for 3 grams, 200,000 of characters isn't enough. And we can see that we should use bigger text only during experiments.
So as far as I remember, the one A4 page is about 2,000 characters, and it means that you have 100 pages of author text to analyze. Is it correct?
Maybe about for all authors, because 200 characters for one author, it's not so much.
I mean, if you have 2,000 characters per page, so in these terms, when you have 200,000 of characters at all from the author text, it's about 100 pages, right? So we just divide it by 2,000.
No, I think pages is less than 200.
Yes.
100. Okay, but it's interesting why we cannot use the smaller amount of pages and the size of the text to make the conclusion about the authorship.
Because we will have small samples and don't have enough accuracy.
Yeah, sure. You will decrease the accuracy, but probably to separate between the different authors, excuse me, you do not need to have 100% significance. So you can lower it, and it would be rather interesting to see the difference. So when we decrease the number of characters, how fast will the significance decrease as well? So probably it could be the future work.
Yes, it can be done in future experiments. We have what to do in future.
Okay, any other questions, please? Vadim has a question.
Yes, if you please. Good morning, everyone. I'm Vadim Ermolaev. I'm here in physical presence at Kherson University, and I'm a bit curious about the idea as well, because the approach is purely statistic, and I wonder if it does work in the same way for different languages. Do you have any experiment to compare Ukrainian samples using these tests and English or French or German or whatever? What would be significance and specificity for different languages?
Yes, this test will work great with different languages because it doesn't depend on the language you choose. It uses only letter combinations, and it doesn't matter which alphabet you will use.
I'm also curious if the sample size in terms of the authors involved is representative in your case. I've chosen only the texts by 10 authors. It's not enough. How would you assess the representativity of your sample?
Then maybe it can be only beginning of our science in this era, and we will have a direction to make bigger samples to make greater representativity in future.
I'm also a bit depressed about the negative test for 3 grams. I mean that if you make the chunks longer, then the specificity, well, due to at least my common sense, has to be harsher. But your experiment shows that it doesn't. How would you explain that, referring to a common sense?
For grams, we don't have enough characters, and to have more representative results, we should increase the number of characters in our corpus text, and then we will have more complete results in this case.
So the sample is not representative for the 3 gram test, isn't it?
It's
at this very moment.
can you repeat your question, please?
Yes, please. I meant that, are you saying that your data sample is not well representative for the 3 gram test?
No, in case of the significance level 0.1, the results are good, but to have significance level 0.05, it would be better to use bigger number of characters.
About this 1.0 level of significance, as a person who uses statistics in real experiments and real data, I've taught myself not to trust this high level of significance. How would you explain this? Why it is so high?
May I comment? I am co-author.
Yeah, sure.
That is explained by the specificity of the area. We mostly work in medicine. In medicine, the 0.95 is the standard significance level, confidence level. The significance level is 0.05. But instead of in literature area, maybe it is just a very high confidence level. But we experimented with 2 confidence levels, 0.90 and 0.95. And we see that then the confidence level is 0.90, we shall very well results. So this is very practical condition. If you have some condition for confidence level, you may stand it at the desired level. And so about 3 grams, maybe the effects of the combinatorial explosion. When we have more letters in combination, the more we see 0 frequencies. And the distribution, because some discrete, maybe discrete.
Okay, thank you. I'm done with my questions.
Okay, thank you. Do we have another questions? I have maybe comment that if you have a text of the author and they use different dialects, then maybe there are some patterns in usage of different letter combinations, but maybe you should use like word connections, like maybe you hear about embedding and vectorization of text when you use n-gram as generalization of n-gram, it's a embedding with vectorization, where you take the letter and a word, and you take words before and after, and you present it as a point in the vector space. And then you try to find some differences in text, like a set of points in an dimensional space. But it's maybe a comment for future directions. Thank you.
It is very interesting comment, because our hypothesis is that this approach is not depend on language. We provided the experiments in Russian literature, English literature, and now Ukrainian literature, and we see some effects of some preferable combinations. So every writer has some style. We can analyze the style using some graphs of dependence between words and so on. But we provide very simple experiment. We use very simple features, combination of literature. This is a uncontinuous feature. This feature of the writer as a person. And we see that this our test differs the text of the same authors and the text of the other authors.
Okay, but maybe I can assume that you will like make some cross languages models. I mean, to compare English-based, Ukrainian-based, Russian-based between them, and to maybe differ them more explicitly. I mean,
yes, we provide some very interesting experience to analyze the Slovo o полку Igorеве. So in old Slovenian language, in Russian translation and Ukrainian translation. And this is very interesting result, but we in future maybe publish it.
Okay, thank you.
Thank you.
If we don't have any other questions, then let's go to next presentation. And oh, okay, we have a question. Did you use any text normalization like lemmatization or stemming, or you just take a raw text?
It was just a text without digitals.
So they didn't use normalization. Okay, yes. So let's go then to next. So I invite Tatiana Sheffer, I think, with a presentation, computational lexicon of Ukrainian discourse connectives, please.
Yeah, actually, Veronica will present it. So.
Okay.
Yeah. So good morning, everyone. So my name is Veronica Solopova. I'm a PhD student in Freie Universität Berlin. And I'm working with Tatiana on compositional lexicon of Ukrainian discourse connection. I'm sorry for the cut. So let me share my screen for the presentation. Here. Can you see it all right?
Yes, we see. Please.
Great. All right. So, as I said, our topic is compositional lexicon of Ukrainian discourse connectives. And the plan for today is to tell you what the discourse connective is, also to explain how we constructed our lexicon, what were the steps for it, then present the final version of the lexicon, and also show you our little pilot study to show basically the reuse potential, where we annotated the 20 texts from different genres to measure the distribution, or like make quantitative and qualitative analysis of connectives there. And we will conclude and see the outlook for the future. For for relevant dimension for discourse level annotation and processing, which is important for us here, is discourse level, which is hierarchical structure of text created by semantic relations between different sentences and paragraphs. So it is also known that discourse relations are frequently marked openly by certain words and phrases called discourse connectives. So here you can see some examples. For example, that discourse is more than just a sequence of sentence, where we see that the same pronoun she will be connected to different persons depending on the context. And then in examples 3, 4, 5, you can see different kinds of discourse connectives. And for example, because and that's why would be causal relationship indicators, and then would be probably temporal one. So note that discourse connectives are heterogeneous class of markers, words of many different parts of speech, as well as larger phrases, which are also possible. And this can play, discourse connectives can also play different roles in different languages. So despite this relatively concise definition, you can see here that it's a fixed word or phrase. Its meaning is a binary relation. So basically it connects and shows relation between two variables in a way. So for example, that X is greater than Y or something like that. And also those arguments are abstract objects, prepositions, facts, statements, and they are typically expressed as clauses. So despite this concise definition, the class of discourse cannot be easily approximated using standard lexicals or morphological syntactical properties as parts of speech. And the reason for this is that discourse connectives are primarily defined by their semantic and pragmatic role. So that's why connectives cannot be captured by post tags, because we can take as an example and, which can be a link between nominal phrases, but can also connect different kind of phrases. And then in most languages, prepositions, particles, and adverbs are usually connectives, but then we have a lot of different prepositions, articles, and adverbs, which are never used as connectives. So this is kind of difficult. So connectives express local coherence relationship, and thus it is increasingly important to incorporate this kind of information from discourse context. Applications are nowadays for them ranging from automatic coherence analysis, authorship analysis, essay scoring, argumentation mining, detection of discourse connectives. Thus is an important area of current research and a valuable contribution which competition linguistics and linguistics themselves still bring into natural language processing. So to enable discourse parsing, as well as linguistic analysis of discourse structure, human-computer readable discourse connectives lexicon have been constructed for several languages, as, for example, German, English, French, Czech, and Italian. Stede, Schaffler, and Mendes presented the multilingual online database Connective Lex, which provides standardized access to all available interoperable discourse connective lexicons in 10 languages. And prior to our work, the only Slavonic Slav language which was presented was Czech, and now we also have the Ukrainian there. Basically, because we didn't have any solid base in the closed languages, we proceeded to our own scheme, and we started from mapping connectives, English connectives to Ukrainian counterparts. Then we filtered and corrected the result. We added syntactic and semantic annotation and applied the lexicon to test corpus and extended the lexicon. So here, more exactly about the steps. We basically took the discourse connectives from Pan discourse 3-bar corpus. Then we also aligned them through open subtitles English-Ukrainian dictionary, and we obtained this candidate list of Ukrainian connectives. This first seed extraction yielded 154 connective candidates, and we then proceeded to ask Ukrainian native speakers to review a list of candidates to decide whether they are or they aren't connectives according to the definition given above, and if so, what are their syntactic properties and their meaning. The native speakers were around 50 participants in a workshop on shallow discourse parsing held at the Office of Grammarly Kyiv by the first author offer in February 2020, so by our Tatiana Shepla. They received, so the participants received brief training on criteria of connectives and lists of the available semantic and syntactic properties. In addition, we provided corpus examples of all connected candidates and which were automatically instructed by string matching from the queued corpus. And thus, also the workshop participants worked in small groups of 3 to decide on each connective lexicon, on each connective. So the work on the second graph consisted on cleaning and the duplicates, removing the so-called Russisms, which are Russian words and expressions which are widely used by Ukrainian speakers but are not considered part of standard language. For example, connective odnako or ili. And for each of the connective, we also additionally reviewed the senses as well as syntactic properties. And this step was carried out by 2 trained linguists, myself and our third author. We had experience in discrete annotation, and we are native speakers in Ukrainian. Also another extra stage was to go through English translation for each connective, and also to add binary columns, continuous and discontinuous connective. So if basically you can put some other words between these connective parts, and also if it's single or phrasal connective, and also orthographical variants of connective. And these 3 columns are basically to match the DIMLEX format. So the final version contained 129 connective, we also completed the list with more connective additional candidates from automatically extracted post-tag dictionary for Ukrainian language. So here you can see the initial basic statistics that we have 14 coordination conjunctions, subordinating conjunctures 49, adverbs 41, prepositions 9, and for other categories, basically all the less representative parts of speech, and altogether 18. Also, we have 120 single word connectives and 35 phrasal connective, and the total was of 129, I guess. So, and this is the XML format, how, like, basically which goes into the website of Connectic Lex Info. There you can, at the same time, so look at different languages and at the same time in Ukrainian and see basically information about each connective. So now we come to our case study, connectives in different media. We basically took 10 spoken and 10 written texts from Mccrae corpus. 10 speeches were from former presidents of Ukraine, and 10 newspapers are texts from Krymskaya Svetlitsa from 2000 to 2020. And we basically compared explicit markers of discrete relations in speech and writing, which is kind of covered in literature for different languages, but wasn't for Ukraine in quantitative style. So we pre-annotated all connective candidates based on our lexicon. We used 3 native speakers, our second, third, and fourth author, to review these candidates, and we also tagged them with PDTB free connective senses. So our inter-annotator agreement is moderate. It's kappa 0.62, and for the senses it's even lower, around 0.48. But again, it's a pilot study, so we will. It's inside us to work on our guidelines and also to do more training with basically all of the annotators. So here you can see our results for speeches. So we measured the results to compare distribution of connectives quantitatively and qualitatively in speeches and articles. We found 597 connective instances in speeches, which is 3.8% of all tokens, and 740 connective instances, which is 3.6% of tokens in articles. This means that articles on average have slightly longer text length, and they still have slightly smaller proportion of connectives. And based on previous research, we expected speeches to have fewer discourse relations, but to use relatively more explicit connectives to mark them. In our data, these two tendencies seem to balance out to yield about equal numbers of explicit discourse relations. For both speeches and articles, even after correction of non-connective occurrences like and, we still have and as the most frequent connective, 162 for speeches and 135 for articles. Then also we have a, which is but, yak, ale, and ta. And they are also among the most frequent for both genres, and as you can see here. Then for articles, however, to and she are also comparatively high in frequency, while she in speeches occur only 6 times, with no uses of to found at all. Another curious difference is that in writing, не тільки алеї is more frequent than не лише алеї. This totally opposite situation in spoken language, which was 1 to 7, basically. Articles also seem to use more connectives related to justifications, like бо, щоб, адже, тому що, наприклад, оскільки. It is worth noting that our annotators were able also to add connective annotations, even when a word or phrase was not previously present in our connective lexicon. And this data-driven way, the annotators identified 50 additional connective candidates. So basically, we will add them in the second version of our lexicon and after validation and improvement process. So now we come to the senses. As you can see, connectives indicating expansion, which is basically conjunction or elaboration meaning, are the most frequent for both speeches and articles. We measured them per 1K tokens. So it's 16.2 against 11.3 connectives per 1,000 tokens. And comparative census class is the second most used. And curiously, articles outrun speeches with 10 to 9 per K tokens. Contingency, which is cause and condition meaning, and temporal connectives are almost equal in distribution for both genres and represent third and fourth most frequent census respectively. It can also be seen overall that expansion relations are much more frequent in speeches than articles, which derive from previous accounts, such as for Italian and English, who observed high frequency of temporal and causal relationship in spoken language. So to sum up, I want to recapitulate that we created this new computer-readable and human-readable annotated lexicon of Ukrainian connectives. We thus found a basis for shallow discourse passing and other applications for Ukrainian language. We also present you an efficient method for creating discourse-connected lexicons based of existing automatic resources. And also we showed you this little pilot study for comparing discourse relations marking in Ukrainian speech versus writing. So thank you for attention, and I'm happy for your questions.
Thank you for a nice presentation. Colleagues, do you have any questions, please? Yes, Alexei.
Thank you. I will jump in. Thank you, Nika, for the nice presentation. And so I'm quite far from the domain, but I'm curious, what about this? So whether your results are open to the public, I mean, whether you integrate this lexicon and results to some open data set, for instance, Ukrainian Brown corpus?
So we didn't still integrate it to Brown corpus, but it is openly, open source on this website we showed, Connective Lex Info, am I right, Tatiana? But it's a good suggestion. I think we have to think of also adding it to Brown corpus and making it more easily to find to wider public. Did I answer the whole thing?
Yeah, I can add to that maybe. So the website that Veronica showed, it's kind of a human readable, right? So for linguists especially, or people who like to compare different languages, that's what it's for, because it has interlinked all these 10 languages. So you could look at contrast in 10 languages. But we also provide just the XML version of the lexicon in GitHub, so you can just download it and use it in, for example, in discourse parsing or so. So oftentimes the first step is to try and find the explicit markers because they're the easiest to find, right? You try to analyze some text, and for that the XML version is perfectly fine, right? And you get all this information. Right now, we don't have a large chunk of data that is annotated with this this information, this connective information. But actually, my student Maria, who's also an author on the paper, she's working on this right now to try and at least get a little chunk of Ukrainian text annotated with discourse relations, so that this can be used maybe for training or evaluating some parser.
Thank you so much for your answer, Tatiana. And the second question, as far as I understand, you started with the English connectors and then find the similar in Ukrainian. But also, have you, probably I missed at this point, but have you tried to find specific Ukrainian connectors, would it be correct to say, that are not present in English, for instance, or I don't know. So I see that there is a function like from English to Ukrainian, but what about some Ukrainian specific words? So how you treat them?
Yeah.
So yeah, I don't know. You want to answer? I think basically that's why this additional level of case study was very important, because while annotating, we also found this additional 50 connectors which were not present. They usually were still the variants or more dialects of the existing ones already, but still that shows us that there is a need of this additional step after just aligning it with another language.
Yeah, so we started from English because that has worked for some other languages before. So there in this website, there's, for example, Bangla, like a South Indian language, or Indian language, and some others, Dutch, right? That were, maybe Dutch is a little closer to English, so you can just transfer everything, right? But we did have already initially the step that we used this conjunction part of speech tag, and we checked all the conjunctions from the Brown corpus, so all the Ukrainian conjunctions from the Brown corpus, to see if they can be connectives. So this we did, right? And we added them before we even did this pilot study. But it's true, there might be, it's a very kind of language specific thing, what can be a connective in a language, because it's not really tied to a word class as such, right? It's really more a semantic notion. So yeah, it might have to be extended, but it's still good to start from something. And you know, the English was just the most evaluated list of connectives that we could find right from this corpus. So
yeah, thank you so much.
Yes, thank you. Any other questions, please? If we don't have any other questions, then thank you for a very nice presentation, and we can go to break, I think.
Thank you.
Okay, good morning, and let us start the second part of our first Ukrainian Natural Language Processing workshop at the ICTERI conference. Right now we will start with our keynote speaker, and it's my pleasure to introduce John Mccrae to the audience. John is a lecturer and researcher at the Data Science Institute and Insight Center for Data Analytics and ADEPT Center at the National University of Ireland, Galway, and he's the leader of the unit for linguistic data. John's research interests includes ontologies, lexicon ontology interfaces, machine translation, multilingualism, under-resourced languages, and many others. Specifically, John leads and coordinates Cardamom project, and which is the main topic for his today's talk. The Cardamom project aims to close the resource gap for minority and under-resourced languages by means of deep learning-based natural language processing and exploiting similarities of closely related languages. The project extends the idea to historical languages, which can be considered as closely related to their modern form, and as such aims to provide NLP through both space and time for languages that have been ignored by current approaches. And for our organizers, for our reason, we think that it's a really good opportunity for the Ukrainian audience to listen for such talk, because still Ukrainian language, if not under-resourced, but definitely low-resourced language in terms of natural language processing. So I hope that John's talk would be of much value for our local community. So thank you, John, for joining us, and the mic is yours, please.
Okay, thank you for the introduction. Yeah, so I'm happy to be talking today. So yeah, as the intro said, I'm here leading this research group on linguistic data, the Cardamom project. So I'm going to talk a little about the Cardamom project, and then I'm also going to talk about a sort of spin-off project we did from this, both of which in the area of working with low-resource languages. So I'll start a little bit by talking about the Cardamom project. So the goal of this was really to combine kind of 3 different areas to try to improve natural language processing for under-resourced languages. So first of all, we looked at big data, things like the linguistic linked open data cloud and the work that's going on there. We obviously looked at deep learning, you know, we're sort of with modern NLP, so deep learning approaches are at the core. But then we're also bringing in the comparative method. So a key idea in this project is not to view languages as isolated islands or individual data silos, but to look at how, you know, related languages can be used and how we can basically use the comparative method of linguistics in order to better improve natural language processing for under-resourced languages. So at the core of it, you know, the problem we're trying to fix is this sort of resource gap that we have for natural language processing. So the idea is if you're looking at, you know, to train a natural language processing system of reasonable quality, you would need, say, a certain amount of data. And it might be the case that your well-resourced European language like German has lots of data, but it's also increasingly the case for some of the major national languages, something like Hindi, as for example, might have a lot of resources and might be over the bar. So really in this project, we're trying to look at these languages that haven't quite got enough resources. Obviously here, located in the west coast of Ireland, where we speak the Celtic language Irish. And Irish is, of course, has a comparatively small population, even in Ireland, so it doesn't quite have the resources. So Irish is a bit below the gap, a bit below this bar, but there's other languages like Scottish Gaelic, which are even less spoken. And of course, you know, very minoritized languages like this one, Pirahan, is spoken in the Amazon. So what we're trying to do is we're trying to both increase the amount of resources that are available for these languages, so lift them towards this gap, but also try to look at NLP methods that require less data. So we're also going to try to lower this bar. So it's both about raising the resources and lowering the bar, so that more languages can get over this gap and have enough resources to build a good modern NLP system. So at its core, we noticed that we use the fact that, say, languages are very similar. So I thought about trying to change this to Ukrainian and Russian examples, where there's a very similar situation, but I'm afraid I don't know very much about Slavic languages. So I wouldn't want to do this. So I'll stick with examples I know, which is Irish and Scottish Gaelic. So they're very similar languages. And what we know is that Irish speakers learn Gaelic very quickly. To be honest, they barely need any teaching at all because they're roughly mutually intelligible. So we basically had the same idea of, you know, can we do the same for an AI? What happens if we teach an AI first? Does it then learn Gaelic better? So we might do something where we take some Irish sentence, and let's say we're doing something like machine translation. Then we'd also take the equivalent Scottish sentence. And what we see in both of these cases is that these sentences are obviously very similar. You don't need to be a speaker of those languages to see that those two sentences really match up in terms of the words. But of course, you should also note that none of those words are actually the same. Every word is different, at least one spelling. So it's not like a trivial case of we can just, train a system in Irish, because the words will be different in Scottish. We need to understand also how the Scottish Gaelic words have changed between these two languages. I said this is something that I think we could also see applying in the context of using, say, Russian training data and Ukrainian training data together. So this kind of transfer learning is kind of really core to the approach that we use in Cardamom. So we're looking at kind of 4 language groups within this project. So we're looking primarily at the Celtic languages and the Germanic languages in Europe. This is because we're based in Ireland, and Irish and English are the major languages here. And so we have lots of trained data, but also, languages with a wide spread of languages. There's some very obviously well-established languages like English and German, and then lots of minority languages like, Frisian and Scots and Bavarian, for example. And also there's a focus on this project also on historical languages. I won't say too much about this today, although I guess there's some interest also in this workshop in that area. But we're looking also at historical language change. So we're looking at old forms of Irish, so old Gaelic forms, and then in the Germanic context, looking at Norse and Old English and historical forms of the languages there. So in the European context, we're looking at these. The other area we decided to look at was the Indian languages. And so there's a couple of reasons for this. One of them is that we have a lot of Indian students in our lab. So we have a lot of people who are very interested in these languages on a personal level. But also another great test case in terms of the languages, of language diversity and language relations. So India has 2 main language families. There's a lot of other smaller language families, but the 2 big ones are the Indo-Aryan family. So this is the Indo-European branch spoken in India. So Hindi is the major language, and these derive from historical languages, particularly Sanskrit and Pali. And then in the south, there's the Dravidian family, which is non-Indo-European, so quite distinct. And Tamil is probably the biggest of these, although they're all quite under-resourced. So, we're looking at we're looking at 4 language families that have, quite different properties, and all present interesting cases where we can use our techniques of transfer learning, because many of these languages are very similar to one another, and they're often code switched among each other, particularly in the Indian languages. Speakers of some of the smaller Indian languages often code switch in Hindi and English, often both in the same sentence, which is very challenging. So how are we going about doing this? Well, our first approach, as I say, is this kind of raising the resource gap. So we're looking at data collection, and we're trying to do data collection from 3 different sources. So first of all, we're continually crawling social media. We're looking at Twitter. We're looking not so much at Facebook because it's difficult to crawl, but we're looking at Instagram and YouTube. And we're bringing data in, on a regular basis from minority language speakers on the web, so as they're using it. And we're also looking at building from the existing academic data sets. And we do this through a portal called LingHub, where we're collecting resources from different catalogs and bringing together. And finally, we're also using web crawls and trying to collect data, from websites directly. And this is all combined through a methodology called linguistic linked open data, and connects to another project I have called Pretalod, where we're doing a lot on this. As I say, for the main sort of scientific method, we're very focused on looking at language change. So here's a great example of a language change where you have a Proto-Indo-European root, PODs, and then we have this, diverging into its Germanic and Latin forms. And we see in the Germanic forms, we get the words, so the modern English word of foot. And then the Dutch word, although again, it's spelt very differently, it's pronounced actually quite similar. This is foot. And then German is Fuß. So you can see, you know, there's obviously similarities. English, Dutch, and German are much closer. There's some similarities, obviously, to the French and Latin forms. And we can model this, you know, as it's standardly done in linguistics by looking at certain sound changes. So we know that consistently T's in Germanics change to S in modern German, and P's change to F in between Proto-Indo-European and Germanic. So these are fairly consistent changes. In fact, it's called Grimm's law. And we're trying to see this, you know, languages not as individuals, but as a continuum with certain changes. Finally, of course, we're looking at word embeddings. So, you know, I guess most people will know this already. You shall know a word by a company it keeps, as John Firth says. So we're looking at words embedded in multi-dimensional vector spaces, and we're trying to learn relationships between them. And, you know, things like male to female relationships and verb tenses come in here. So obviously this is then based on deep learning. So I don't know how much I need to explain this to this workshop, but you know, the idea is we use artificial neural networks with kind of hidden layers which have this kind of deep connections, and then we learn these weights through usual approaches like SGDs. So the idea of this is to bring it into kind of a deep polylingual model. So a lot of the ways we're approaching this is by learning on multiple languages simultaneously. So the idea is if we're looking at, say, our Germanic languages, we'd be learning on English, which maybe has lots of data, and Dutch, which has less data, and then minority languages like Frisian, which is spoken in the Netherlands, and Old English, which is the historical form of the language. And what we'd see is that we'd be able to learn a single vector model that kind of maps all these words to similar spaces. So, you know, simple words like water, which have a similar form in all three of these languages, would have a similar space, and related semantic words would come in here. So, example here, of course, is that the word dog is only in English. The other languages use some variant of the English word hound, so we'd know that that is sort of in the same space, also partly because we have the English cognate also still used with a slightly different meaning. So that's the goal. So we're trying to combine this kind of dynamic word embeddings, automatic dictionary construction, and distributional hypothesis. We're looking at you know, building studies that look at languages changing over very long periods, so centuries to millennia, and models that use the phonetic form. So we actually care a lot about the word, how the word is written in the process of building our word embeddings. So where are we applying this? So, well, we have linguistic analysis tools, language identification, and morphosyntactic analysis, including looking at code switch analysis. So we published on sentence level language detection at Coling last year, and we're now working on doing code switch language detection. We're also going to make some kind of great tools for lexicography and for language learners. So I think it's an important part, particularly for many of the minority languages like you know, Irish in our context, that we look at how we can improve the usage of that language by how it's learnt. I'm also very interested in historical languages and building workbenches for digital humanities. And there's one of my PhD students looking at a very old manuscript. So I'm going to talk about a project that we kind of followed on from this. So this was in the context of one of our research centers, ADAPT, and we were working with a company called Translators Without Borders, who developed vocabularies for aid workers working in crisis situations. So what they basically do is they basically provide translations, particularly looking at these minority languages. So an example is sort of the Haitian. In Haiti, there was the earthquake in 2012, which devastated the country. And lots of aid workers came in and then realized that they had trouble communicating with the locals because there was virtually no resources about Haitian Creole. So this charity is there. It's a non-profit that develops resources for aid workers, and they came to us and they were like, well, we want to improve this using open data. So we looked at open data that's available, like WordNet, Wiktionary, and Wikidata, and we tried to build ways to improve their resources. So the particular area we were looking at is related to the Rohingya refugee crisis. So this is due to the genocide that's going on in Myanmar, has displaced over 200 million people, and the largest number of those are actually displaced into Bangladesh, this neighboring country. And Bangladesh is itself, it's a fairly linguistically diverse country. It has its national language called Bengali or Bangla. But this has a number of dialects that are barely mutually intelligible with the main form. And in particular, of course, the refugees coming from Myanmar are mostly centered here in this green area, which has a dialectal language form called Chittagonian. So we're looking then at 5 languages. We're looking, of course, at English because this is the language the aid workers know. Bengali is the national language. Burmese is also going to be useful because it's where most of these refugees are coming from. Chittagonian, which is, of course, it's a big green area. And also the Rohingya, in fact, have their own language. So Rohingya often, the speaker form, again, related to Bengali, but different again. So what we were doing was we were trying to build these glossaries up and extend them, the existing glossaries. So it's important, for any aid program that, that they have the language so they can speak with the locals. So these TWB's goal is really to provide this kind of list of localized emergency related terms. What we wanted to do was to kind of increase the number of terms, and we wanted to kind of help to discover associated terms which might be useful, which might be priorities to find translations in the local languages. So in fact, the glossaries, they look something like this. They're actually, they're really simple. They're basically CSV files with just the words. And you'll see, all kinds of vocabulary, from basic general vocabulary like month names, and then things that are maybe useful in kind of an educational context and so forth, and lots of kind of health-related terms as well. You also see, of course, that we have an issue with scripts as well, because obviously Bengali and Chittagonian are written in the Bengali Assamese script. Myanmar there's a Burmese script. And Rohingya is actually mostly written in Latin, and this is actually because most Rohingya are illiterate. So a lot of the resources have been sort of developed by well-meaning foreigners and written in Latin script rather than the Bengali Assamese script that is more common in this area of the world. So that's an interesting aspect as well. Okay, so to do this, first of all, we started working at the corpus. So for English, Burmese, and Bengali, English, Burmese, and Bengali. This was very easy. We just went to all our usual sources: Wikipedia, the Opus Corpus collection, Curl, which is University of Leipzig's corpus for under-resourced languages, and we found lots of text. So that was easy. Rohingya was quite challenging, but we found a very small corpus, mostly based on translations of the Quran. And for Chittagonian, well, initially we found basically nothing. And then we looked a bit harder and we found a tiny bit of Bible translation. So we use that Bible translation as a bootstrap in order to then go through Facebook and YouTube and try to find posts that contained distinctively Chittagonian words. And we used this and we put together, a corpus of Chittagonian, which is actually the first digital corpus at all, because there was nothing we could find on the web beforehand. So to give you an idea of the size of them, the Bengali and the Burmese corpus were both over 10 million words. Rohingya, we got about 100,000 words, but for Chittagonian, we're still struggling in the tens of thousands of words. So, the amount of text we have, just plain text, completely unannotated, is quite small for some of these languages. So we approach this primarily actually through linking these with other resources. So the idea is we connect their glossaries through the English with, say, Wikidata and English WordNet. So, that will then give you access from Wikidata to Wikipedia and the linked Open Data Cloud. And English WordNet connects with things like the Open Multilingual WordNet, so translations there, and the Alexis Project's resources. So it's basically this kind of English monolingual linking. We did this using a tool we've been developing for a number of years called the NASH system, NASH being an Irish word meaning links. And NASH is a kind of pipeline approach where we try to take two data sets and discover kind of where they have the same things in them. So in this case, we're looking for the same words, but we also use it for things like ontologies and knowledge graphs to try to integrate them, from different domains or different business areas. So NASH is a strategy of using some initial blocking goals to try to find an early kind of set of candidate matches. And then it does NLP analysis, so it does text extraction and then text feature generation. But it also does graph analysis. It also will look at how words are related. So, using things like WordNet, or, if we're looking at resources like Wikidata, there is a kind of graph nature to it. And then we do a kind of machine learning step. And then we do actually a constraint satisfaction step, because it's important in linking that these make sense. We don't link everything to one entity, and we try to make a consistent overall linking between these tools. So this is basically the idea of how we built the system. And we used a lot of features that are fairly standard. First of all, we used this kind of battery of straightforward text features, so things like longest common subsequence, Jacquard and Dice of the words, Levenstein, and so forth. And then the other approach we used was a BERT-based Siamese deep neural network, which kind of compares the similarities using the sentence BERT model. So when we put this together, we got overall quite strong results. One of the odd things we got was that actually the less sophisticated our method, the slightly better it seemed to do. Our overall strongest result was to use just the plain text things rather than the BERT similarities, and to apply this without much kind of fine tuning. So if we just let the model use its unsupervised mode, that seemed to do a bit better. But all the results are pretty close. We're kind of about 80% in our accuracy, which kind of coming back to the use case is something that is good enough that the aid work or the terminologist can work with it and can build on this. So to give you an example of some of the kind of informations we'd get, we would have our corpora resources, so we'd give them examples of usages in the target languages, and we're giving them things like alternative definitions, new terms that they could consider, so expanding the English side, related terms, which could be useful, translations coming into new languages, so they could add German or French very easily. Images were very important because, as I've already said, a lot of the people who they're working with are illiterate, so adding images would be very useful for them. And of course, the Wikipedia articles would be a nice thing to help explain these terms more. We then built this into an application. So the idea is it's simply a kind of checkbox kind of thing, where the terminologist could review these terms and decide whether they wanted to add this into their resource. So we built this up using a technology stack based on Sparkle and Apache Jenna. So we also included some kind of language identification work. So this is the decoding work. And what we did here, which was quite interesting, is that we looked at two very challenging data sets. So first of all, we looked at the South African Bantu languages data set. So this is a group of 11 languages. 2 of them are Indo-European, but the other 9 are roughly mutually intelligible. So, something very close to each other. And then we actually looked at Swiss German. So this isn't distinguishing standard German from Swiss German. It was actually to do with individual dialects within Switzerland. So these are very close languages, and they're very challenging to identify. And we actually found that we could improve the performance, quite significantly. So compared to the best model, we're much better in terms of this. And we even looked at doing this in a fully unsupervised mode. So we had a supervised training where we knew what the languages are, but we also just said, there's 5 languages here, go find them. And we found that we're surprisingly okay at this. So we can get some reasonable performance just looking at languages without any initial training data, which of course is quite useful when we're looking at big web corpora and we don't even know what the languages are. So overall, this project came out, and it created open resources that can improve the data that TWB have, and we could do this even though these languages were very under-resourced. As I said, our naive initial searches for Chittagonian data found nothing. We had to really struggle to find Chittagonian data. So this was something very important, and we could use this to develop resources. Probably the biggest issue is actually that there were some issues with kind of the candidate matching, that we couldn't always. Some of the TWB terms simply didn't match to anything in Wikidata or WordNet, or they matched to something completely irrelevant, and that was a big challenge. So that's probably a good point to stop. So in summary, we're looking at the Cardamom project is looking at kind of building things that help society. A billion people in the world speak a minority language, and we're trying to help them, help these communities, trying to help people to learn new languages, to get into contact with their history, and kind of build society at all levels. So we're doing this through natural language processing, looking at deep polylingual models, and bringing the comparative model in more majorly into modern natural language processing. But also we're hoping to then connect this with digital humanities and provide new resources and new tools, and new kind of analysis methods based on kind of distant models of reading text, in order to improve sort of how humanities work. So that's everything. So thank you, and I can take some questions.
Thank you so much, John. Thank you for this overall overview of your different projects. It was really interesting. So, dear audience, do we have questions to John? Please raise your hand here in Google Meet. So while waiting for the questions from the audience, John, I'm really fascinated about this idea of having word embeddings for multiple languages at once. So probably I will try to narrow my question, but first of all, what are the main issues while training word embeddings for multiple languages?
Mm-hmm. Yeah, so I mean, there's a few approaches that have been done. So one thing that was there's kind of two ways to approach it. One is to try to do it simultaneously, which is quite challenging because often the model will understand that there are two different languages, and just you don't get that you don't get the relationships coming out because the model just ends up basically separating the two vector spaces out. So one thing that the other approach is to train separately and then align later, often using a method called procrustase analysis, where you try to align one vector space or map one vector space into another. But then you're always sort of trying to basically project one language into another's space. So a big challenge is when you're training this is to try to get a model that will be learning together. So, taking features of both languages while it's learning. But then, actually, getting some kind of similarities between those languages and building that connection, because there is a tendency for it just to see it. If you just naively train like a machine, you take a word to vec model and you just stick in some say Russian text and first some Ukrainian text, then it will learn a Russian space and a Ukrainian space, and it won't learn very much between them, other than maybe any cases where the lemmas are the same. So that's a kind of a challenge. Quite how you do this, and build a, encourage the models to try to learn together and try to map these into the same space.
Okay, thank you. And there are some words that like the same word, but in the different language they have a totally different meaning. I mean, it's like this. If you take the sentiment, it would be like one total different sentiment. And I can, from top of my mind, take words from Ukrainian and, for instance, Czech language that they have totally opposite meaning. So it's interesting how this kind of cases could be treated in this word embedding if they have the same vector space and you have the one word, and then what would be the behavior of this word in the vector space, if I may?
Yeah, it's a good question. So I mean, these kind of issue of false friends is certainly a challenge. And when you have closely related languages, you often get this. The word has shifted meaning in a subtle way. But I would also want to, you get this even if you're looking at a single language. A word like, say, the English word wicked, as an example, can have both very positive or very negative meanings with seemingly no distinction. Wicked can be great, or wicked can be evil or wrong, So these kind of semantic, and it's often caused, particularly in closely related languages, by semantic shifts. The words are related, and therefore our methods of looking at, the kind of comparative changes will try to associate these words because it knows that they're, morphologically or orthographically related. So it is certainly something that is an issue. At the moment, my attitude is a little bit that it's a case of I don't think it's frequent enough that it's something we necessarily need to fix. But this is certainly a weakness of the method, that it would see these false friends and get tricked by false friends. When you're looking at modern language, that's kind of unavoidable. So it's certainly a challenge.
Yeah, thank you. And we have a question from Yulia Mccorma. So Yulia, please go ahead.
Hi, John. I have a question about, maybe I didn't understood it from the talk, but how do you handle the multi-word sequences? So if you have, we know that sometimes you have not only many words of a phrase, but sometimes they are like in some distance in a text. So if we have the constructions that are like spread through the sentence. So what can you do in this case? And I have also the other question about phonetics. Maybe you can say, did you use it? Did you try it? Could there be any benefits of using the phonetical representation? Thank you.
Okay, very nice questions. So multi-word expressions, obviously we do look at this. So, as in the context of kind of modern NLP, we're using models, contextualized models like BERT, but understand, not just a single word. We have word embeddings as the base, but then you also have the encoding model, which understands how these compose. So multi-word expressions come in, obviously, through the use of models like BERT. And, some of our systems are by nature like the linking system, the Nash system I presented. I mean, that works with multi-word expressions anyway. It's always been designed this way. We obviously don't particularly develop embeddings for multi-word expressions. I know there's a lot of interesting related work. Particularly there was a Parseme project on multi-word expressions, and I co-organized the multi-word expression workshop a few years back. So there's a lot of interesting stuff here. It's not a particular focus of this project, but it is certainly interesting. Your second question was about the use of phonetic representations. So this is something we've looked into, actually. Particularly, we looked into it in the context of our Dravidian languages, where they're written in their own scripts. And most of these Dravidian languages actually have a unique script. So each language has its own script, which meant that trying to kind of naively apply our kind of orthographic approaches doesn't work, because they're using different letters, and often these scripts are actually very different. So in that case, because of the nature of these languages, we looked at mapping it to a phonetic space. And what we found was that you have to get it kind of just right. So we started off by using the International Phonetic Alphabet, because that's the standard for representing phonetics. And it turns out that was not much better than not doing anything at all, because there were just all of these subtle differences in the pronunciation that we kind of didn't want to really capture. Vowels that are maybe fairly close, but of course they have a different symbol in IPA, and small changes in the extra kind of things like aspiration marks and such like that came into the IPA that really caused problems or caused challenges for our machines. So we found with phonetics we had to do a kind of more of a, what we used a sort of Latin Romanization phonetics, which was much rougher, but that actually worked much better because the similarities between languages seem to come out more when using a more rough level of phonetic transcription rather than the sort of more correct one. And that was certainly something that helped. Now we're also looking at this in context of languages that do have the same script, but sometimes it helps and sometimes it doesn't. I mean, I think an obvious example is sort of say French to English. French and English have a lot of words that are orthographically written the same, but the pronunciation is very, very different between the French and the English pronunciation. So often phonetics can kind of, particularly if it's done too precisely, can actually, hide things that are more obvious from the orthographic representation.
Thank you. I'll be waiting for another questions. I have another one. So it's interesting how we can use this approach specifically while studying historical languages. And so can you bring some examples of the research result while using Cardamom project? For instance, I'm curious whether it's possible to measure how the particular word change during some time in terms of historical perspective. For instance, if we try to compare its neighborhood in vector space again, have you tried some kind of this stuff?
Yeah, so I mean, this is something we're also looking into very actively. Particularly, we're looking at this in the context of changes in the Irish language, where we have a long historical corpus, and you get these kind of semantic shifts. But one particular challenge we're again getting is orthographic changes. So tracking a single word, particularly when you're looking at it over the context of hundreds of years, is actually quite challenging because the spelling will keep shifting and the way it's written. And obviously, as you go back into more historical corpora, you also get a lot less consistency in the spelling. I think the idea that a word only has one spelling is surprisingly modern. So, we have a lot of variation, and understanding all that variation as well with the challenges of looking at semantic shifts is quite difficult. Another thing we have been looking at, of course, is also dating of text. So there's a lot of historical text that we have in archives, in libraries, but we don't actually know how old they are. We only have rough guesses. So another interesting aspect is looking at the trying to figure out the date and using the linguistic features and trying to understand which linguistic features correspond to which time, and try to better date some of the texts, and even understand some of the questions of authorship as well. So, again, we often know nothing about who wrote a particular bit of text, historical text. So trying to understand, does this seem like a single person writing, or are there the characteristics that would suggest there are multiple people behind this text? Is also something that we're looking at. So there's a number of interesting things in historical linguistics fronts that we're kind of developing systems for.
I see. And have you tried to train, again, the word embeddings for one particular language, but from different historical perspective? Let's take for Irish, for instance, when it's a common vector space, but from different historical periods. And if yes, so how you then differentiate between, different different years or historical. So in my vision, it's like we have this additional historical feature or axis that we need to stick to. So how do you deal with this?
Yeah, so I mean, in practice, our experiments, what we do is we break our corpora up into a number of different folds, basically. So historically, so we'll have, say the first 50 years and then the next 50 years and so forth. And we've been doing exactly these experiments, looking at the different sections and seeing, if we train a model on, say, more modern version, how much loss in terms of the performance of our models do we get when we're looking at an older section. And we get a nice correlation. Obviously, the more recent the text is, the better it performs. But there's also a lot of variation within that as well. Like, a particular, you might look at a particular 50 years, and then for some reason that's much harder, just because of the text, being harder. A particular challenge in working with historical text also is that there's a lot of verse rather than prose, and NLP on verse is very challenging. So this is something that is does mean that sometimes we get odd results, but it's certainly something we're looking at, and we're looking to see how you can train a language with sort of time as a parameter, so that you could change it and even potentially try to change that parameter so that you're looking at what the language might be like before your corpus exists. So can you go back to the kind of prehistory of the language? That's something we're really interested in looking into.
Yeah, thank you. Oh, we have a question from Oxy. So Oxy, please.
Yes, thank you. John, you mentioned that Gaelic speakers are talking, they're learning fast. But I have a question about talking patterns. I mean, for me, English native speaker, English speakers, they are talking too fast, very fast. Yeah, is it the problem for speech recognition machines or not? I mean,
yeah, definitely. Yeah, so speech recognition is obviously yeah, so I mean, speech recognition, can be strongly affected by the speed of the speaker. Also, of course, things like background noise, all of these things come in. For speech recognition, a well-recorded session with a nice microphone against, two people chatting in a cafe will be much different in terms of its performance. So this is certainly a challenge, yeah.
And probably we're running out of time, and I will ask probably the last question. So, John, this bunch of projects you're working on, are you open to what kind of collaboration are you open to? So, for instance, you mentioned that your group lacks this experience probably with working with Slavic languages, and here we want to establish research in particular Ukrainian, but not only, because, for instance, in Ukraine we have other native languages, for instance, Crimean Tatar language, which is under-resourced, obviously. So are you open for any collaboration, and how it
definitely always happy to collaborate? And actually one of our team members is Russian, so we do have one team member who has some experience in this and knows this area. But yeah, we're always very interested in collaborating and seeing how our methods can be applied, in different contexts, So certainly. send me an email.
Okay, great. Thank you so much. And
okay, thank you.
Thank you, John, for having time joining us. It was a great pleasure to have you here.
Okay, thank you very much.
So, and then now we move on to our next speaker. And the next paper for the UNLP workshop is titled Estimation of the Local and Global Coherence of Ukrainian Texts using Transformer-Based LSTM and Graph Neural Networks. So, Artem, are you ready to start your presentation?
Yes, thank you. Good afternoon. I will share my screen.
Yeah, please go ahead.
Yeah.
And you have roughly 20 minutes for a presentation and then a Q&A session.
Yeah, okay, thank you. Can you see my presentation?
Yes, everything fine. Please go ahead.
Okay. So good afternoon. Let me introduce myself. My name is Artem Kramov. I am a postgraduate student at Taras Shevchenko National University of Kyiv. Topic of my presentation is the estimation of the local and global coherence of Ukrainian texts using transformer-based LSTM and graph neural networks. Firstly, let's consider the essence of the problem. The coherence evaluation of a document falls into a category of natural language processing tasks. A text coherence implies the semantic integrity of its components. It simplifies the perception of the source of an author by a reader due to the availability of logical connections between the different parts of a document. More coherent document is easier to read and understand. Let's see some trivial example in order to understand it. This slide demonstrates a short excerpt. The first 3 sentences are grouped around the same topic, some schedule. However, the topic of the last 2 sentences doesn't correspond to the previous one because it describes just weather and some opinion about it. That's why together this short excerpt is incoherent. Take into account the variable size of human text from several sentences to several thousands of sentences and more, it is advisable to consider the coherence of a document at different levels. Local coherence implies the consistency of neighbor spans of a text, like sentences or some discourses. In contrast, global coherence implies the availability of such connections between the remote text spans within a whole document. For instance, the first 3 sentences and the last 2 sentences are coherent according to the local coherence. However, this whole short excerpt is incoherent according to the global coherence. The availability of such features of coherent document causes the utilizing of this property of a text for solving different tasks. For instance, it's utilized for the abstract-to-text summarization in order to ensure that the generated text is readable and can be understood by a human. Detection of the symptoms of mental illness in order to detect the deviation from the topic during the analysis of speech of the patient. Creation of post-learning materials, guides, articles, or even automatic extraction of information from structured and unstructured data sets in order to reveal the text spans that contains some information like a title, short descriptions, and some others that can be understood by a human. It should be mentioned that the coherence evaluations falls into a category of AI complete tasks, artificial intelligence complete tasks. It means that the coherence evaluation cannot be solved just by utilizing some traditional classical algorithm. That's why most modern approaches are based on machine learning techniques, namely deep learning models. Most state-of-the-art papers are devoted to the analysis of English corpora. The same investigation for Ukrainian corpora is still at the initial stage and requires further investigation. That's why the goals of the work are the following: designing experimental application of the effectiveness of transformer-based and LSTM neural networks for the estimation of the local coherence of Ukrainian text. Investigation of the connection between sentences during the local coherence evaluation, because it is really important to understand which features of sentences should be taken into account in order to estimate their consistency. Designing and experimental verification of the effectiveness of a graph neural network in order to estimate the global coherence of Ukrainian documents. Firstly, let's start with the local coherence estimation method. The input data of the method, namely an input text, are presented as a set of the clicks of fixed length, L equals 3. Therefore, the input text T is represented as a set of clicks S sub 1, S sub 2, S sub 3, S sub 2, S sub 3, S sub 4, and so on, where S denotes a single sentence. The output coherence estimation value is calculated as a product of the coherence of all clicks. That's why the main goal of this method consists in the estimation of the considered probability. In order to calculate this measure, the model based on neural network layers was designed. This slide demonstrates the main components of the suggested model. Firstly, each sentence is passed through the preprocessing block that performs tokenization, lemmatization, and the vector representation of each word of the input sentence using the pre-trained semantic embedded model ELMA. Then this set of vectors is passed through the sentence model. This component should be considered as the main block of this model because it performs the sentence vector representation according to the expected consistency of these sentences. In order to implement this block, two different architectures were utilized: LSTM cells and transformer-based architecture. As LSTM cells are widely utilized in other state-of-the-art approaches for the coherence simulation for English corpora, it was also decided to utilize the transformer architecture for the following reasons. Firstly, it's availability of positional encoding and the self-attention mechanism that allows revealing dependencies between different tokens regardless of their positions within a sentence. We suppose that it might be crucial for Ukrainian corpora. Then the output vectors of sentence models are passed to the binary classifier. Firstly, these vectors are grouped into a common vector using concatenation layer, and the resultant vector is passed through the set of dense layers. The output of this binary classifier interprets the probability of the coherence of this input click. This slide demonstrates the results obtained for different sentence models based on LSTM cells and transformer architecture. In order to estimate the accuracy, two different tasks were solved. The first one is sentence ordering task that consists in the detection whether the model is able to distinguish the original version of a document from its changed versions created by the permutation of sentences positions. The insertion task consists in the detection whether the model is able to detect the original position of a sentence that was previously extracted from a document. These tasks were solved on two different datasets. The dataset number 1 consists of news articles just from a single news portal. The dataset number 2 incorporates documents of different types: news, blog posts, articles of the National Academy of Science of Ukraine, Ukrainian literature. As can be seen from this table, it is advisable to take into account the word positions at first while estimating the coherence on considered datasets, because the accuracy of the sentence model based on LSTM cells outperforms the other suggested approach. Then the next chapter of our paper is devoted to the analysis of the sentence representation, because it is necessary to understand which sentences are grouped together, which sentences are considered as consistent according to our designed model. That's why all the outputs of the sentence model, namely the vectors of sentences, were projected into two-dimensional space using UMAP dimensional reduction technique. The achieved result is shown on this slide. So there are 5 different clusters. Let us consider which sentences each cluster incorporates. This slide demonstrates the central points for each cluster. After the analysis, more detailed analysis of each cluster, it can be concluded that the cluster number 1 consists of full quotes with mention of an author. The cluster number 2 incorporates just references to the source that is typical for news articles. Cluster number 3 is the biggest one and contains the sentences of different topics, politics, sports, science, etc. Cluster number 4 and cluster number 5 incorporate the beginning and the end of quotes correspondingly. That's why it may be concluded that the designed model considers the structure of a document according to the text of some training corpus at first, while estimating the consistency of these sentences. However, after the analysis, deeper analysis of the cluster number 3 that is described in our paper, it was revealed that there are different types of connections between sentences within this cluster, namely semantic connection, first-person narrative, common phrases, common dates, and so on. And that's why, despite of the utilizing just the semantic representation of discourses in other state-of-the-art approaches for the coherent evaluation of English corpora, may be concluded that it is advisable to utilize more text features in order to improve the accuracy of the design coherence estimation model, I suppose, for English and for English, Ukrainian, and other languages. The next chapter of our paper is devoted to the creation of the global coherence estimation method. In order to take into account remote connections between sentences, it was decided to represent an input text as a graph, where each vertex corresponds to a single sentence and edges interpret the connections between them. The main steps of the suggested method are the following: establishment of the edges of the directed graph, calculation of the weights of edges, and coherence estimation based on the graph build. In order to implement the first step, namely to establish edges, it was decided to perform the experimental verification of the effectiveness of other graph-based coherence evaluation method named semantic similarity graph on the value of its regulative parameter theta. Semantic similarity graph methods consist in the representation of a text as a graph, where also all sentences are represented as vertices, but the edge is established between two nodes if the weight of this edge is more than the value of regulative parameter theta. As can be seen on this slide, there is the dependency on the accuracy of the solving sentence ordering task on the value of its regulative parameter. And the highest value was achieved for the value of the regulative parameter theta that is equal to 0 and 0.1. It means that it is advisable to take into account the connection between all sentences during the analysis of the global coherence of the document. That's why our text graph is cyclic and complete. In order to implement the second and the third steps, namely the setting of the weight of edges and the evaluation of the output coherence, was decided to design a neural network model based on layers of graph convolutional network. Firstly, all node vectors are initialized utilizing the previously trained sentence model that was taken from the previously considered method. Then the update of the vector presentation of vertices according to the GCN is performed by the following equations that's shown on this slide. M sub I denotes the influence of other vertices into the current one. E sub ij denotes the weight between two vertices, I and j. This value is calculated utilizing a set of separate dense layers. The vector representation of a vertex is performed according to the influence of other vertices and its current state. Readout function, namely the aggregation of all vector representation of all vertices into the common vector representation, is implemented as an extra LSTM layer in order to take into account the sentence positions of the input document. The last one is the classification model, the last block that is implemented as a simple binary classifier. The output of this classification model interprets the probability of the coherence of the whole document. This slide demonstrates the results obtained for the sentence model based on LSTM model, namely local coherence estimation, and graph neural network, namely global coherence estimation method. The results obtained indicate that the local coherence estimation model outperforms the corresponding global model on datasets number 1 and number 2. However, the more detailed analysis of the overlapping percentage of correctly recognized documents for these models on the considered datasets indicates that it is advisable to consider the effectiveness of these two models on different datasets, because the overlapping percentage doesn't exceed 40%. It means that these models are able to correctly process different types of documents. That's why two different datasets, number 3 and number 4, were created from the datasets number 1 and number 2. These datasets, newly created datasets, just contained the text with a count of sentence from 3 to 6. As can be seen from the results, the global coherence estimation method outperforms the local coherence estimation method, except for one case. That's why it may be concluded that it is advisable to utilize the designed both global and local coherence estimation models for different directions. Local coherence estimation models may be utilized in order to track the change of the consistency of neighbor text spans within a whole document by the consequent analysis of this document. According to the global coherence estimation model, it may be used for more detailed analysis of some particular part of a document in order to reveal the dependency between all sentences of this excerpt, paragraph, and so on. According to the results obtained, the following conclusions can be drawn. The results of the comparison of the use of different neural network types while estimating the local coherence may indicate the appropriateness of taking into account word position within a text while analyzing text spans for the coherence simulation of Ukrainian corpora. It should be mentioned that we performed the same analysis for the Slavic language, namely the Polish language, and the results were the same. The analysis of sentence representation by the component of the suggested method allows drawing a conclusion about some structural consideration of sentences by the designed coherence estimation model at first. However, more detailed analysis of the biggest cluster might indicate the availability of variety of other types of connections between sentences, like semantic, common phrases, common days, common person, and so on. The negative dynamic of the change of the accuracy of the semantic similarity graph method during the increase of regulative parameter may indicate the availability of the connection between all sentences during the global coherence estimation of the considered Ukrainian language corpora. In general, the results obtained for global and local coherence estimation models indicate the advisability of the usage of them for different purposes while analyzing the coherence of Ukrainian documents, namely for the analysis of the text parts of different size. Thank you for your attention.
Thank you, Artem, for your presentation. While we're waiting for the questions, and the audience, please raise your hand if you want to ask the question to Artem. I will want to start. So, Artem, can you please jump into the slide with the model, with the architecture of your first model when you have those clicks and yeah, this one. So first, my first question, just to clarify the terminology we use. So what is the click in your paper? What does it mean?
The term click means the group of sentences of fixed length. Each click contains the sentences according to the positions in the sentence, like the first, the second, the third sentence, the second, the third, the fourth sentence, and so on.
So is it correct to say that it's a sequence of sentences that which goes one after another, right?
Correct.
And you mentioned that the size of the sentences are fixed in terms of the words.
No, it was decided to. Yeah, of course, it was in order to speed up the training process. It was decided to perform some padding mechanism in order to train it using batch technology, and we decided to, as far as I remember, we decided to utilize the max number of words that is equal to 40, according to the investigation of the other English corpora, that more words in a sentence is almost always can be understood by a reader fully, in a full manner.
Yeah. So have you limited the number of words in the sentence for your specific model, or we can use different lengths of the sentences?
We've limited the number of words because just for the speeding up the training process.
Okay. And probably the second question regarding the architecture, as far as I understand, you fix the number of the click length to 3, and it means that you just measure coherence within this window of 3 sentences. And obviously, if we take some news article, and as far as I understand, one of the corpora you used was Ukrainian news articles, it's easy to find the cases when these incoherent sentences would be in the different part far enough, like, I don't know, 10 sentences, for instance, or much farther. So how do you plan to deal with this? Because this kind of architecture have this limitation that we stick to this specific length. And what are the opportunities, how we can tackle this challenge?
First of all, we decided to utilize such a length according to the to other state-of-the-art papers. And in that papers, different lengths of these clicks were utilized, and it was revealed that the accuracy remains almost the same. According to the detection of some long-distance incoherent cases, as we can see from the previous slide, we calculate the output coherence as a product of the coherence of all clicks. So if we will detect that some neighbor sentences are not consistent, then the output mark, the output measure of the coherence will be lower.
Okay, thank you so much. We have a couple of questions from the audience. So, Oleksiy Turuta, please.
Thank you for presentation. I have a question on slide 7. Could you wrote about transformer-based methods. Could you say what kind of transformer-based methods did you use for debug?
Yeah, thank you for your question. We have utilized just the classical approach, classical realization, implementation of transformer. We used 2 encoders, and each, as far as implements, number of head is equals to 8. So we didn't utilize some already some implemented solutions, because unfortunately for that time when we started this research, such models were absent, but I know that now they're presented. So it was decided just to implement the transformer from scratch according to the original paper.
Thank you.
Thank you. And another question from Tatiana.
Yes, thank you. Thank you for the presentation. I have a question about the aggregation of the individual scores for the local model. So I think you showed that you multiply, you get these 3 scores for the 3 sentence chunks or clicks, and then you multiply them. Did you try other ways of aggregating this? Because, for example, if you think of your initial example that you showed on the slide, there's 1 break, but the other parts are locally coherent, right? But if you get this and you multiply in this very low number, you'll get a very low score in the end, right? So just a few breaks will really lower your coherence score overall. And I wonder if that's the right way to kind of aggregate these different individual scores.
Yeah, thank you for your question. First of all, we can always apply some route according to the number of clicks in order to make our value more normalized. And according to the multiplying, it was decided to utilize this operation according to other papers, other approaches, in order to reward negatively such cases when some sentence deviates from a topic. When it is necessary, for instance, it may be utilized as I said before, for detection of mental illness symptoms, when some person is talking and suddenly he interrupts his speech with other sentence that is totally with other topic, and the multiplying mechanism allows us to negatively reward these cases and to lower the output coherence measure.
Thank you.
Thank you, Artem. And I want to ask another question regarding the Ukrainian, how can I say, Ukrainianish of your topic. So your presentation seems like totally agnostic of language. You just mentioned once or twice that you use Ukrainian corpora. It would be great to see the comparison of this approach regarding different languages. So have you tried to, because I assume that you work with, for instance, English, and then tried to use it for Ukrainian. Have you tried this one?
Yeah, thank you for your question. First of all, we tried utilizing the same approaches for other Slavic language for the Polish corpora. The main difference was that for the sentence models, for the transformer-based approach, we utilized the pre-trained BERT model. And as I said, the LSTM-based approach was also better in comparison with this BERT model. We thought that it will be that the BERT model will outperform, but the LSTM model leave the best. According to other languages, we tried our other approaches to analyzed to estimate the coherence of English, Chinese, and Arabic corpora. But that approaches was devoted to the analysis of the coreference resolution, the impact of the coreference resolution on coherence evaluation. And according to the utilizing of the considered methods, we decided not to utilize them on the English corpora because because the same approaches have been already implemented for it.
Yeah, I mean that you obviously you cannot, so you're not obligated to run it on English corpora, but still you can compare the results published by other authors. And also, because we're running out of time, my last suggestion probably would be, it would be great to see more information about your used corpora. For instance, you mentioned like 2 of them in one moment and 4 of them another, and on another slide. So whether they are opened, I mean, so do other researchers can play around with your corpora and replicate your results?
Yeah, unfortunately, I'm not sure that I'm able to share it in public access because it's some articles of news portal, and it's the first data set, and the second data set was kindly provided to me by other persons that asked me not to share it with others. So I can just share it in a private mode.
Yeah, so and you understand that it's hard to estimate the quality of the results if no others can reproduce them. But you're probably familiar with open Ukrainian resources, for instance, published on Lang UK portal, and there is also a corpus with Ukrainian news texts. They just shuffle all the words and all the sentences, so it's almost impossible to figure out what are the sources. So I mean that probably for the future research, it would benefit your results if you use those open corpora. It's just a suggestion. Thank you for your research and thank you for your presentation. And last but not the least, we have Oleksiy Turuta from the Kharkiv National University of Radio Electronics. And their group of researchers presents the paper titled Ukrainian Use Corpus as Text Classification Benchmark. So Oleksiy, please, the floor is yours.
Thank you, Oleksiy. I would like to present my paper, Ukrainian Use Corpus as Text Classification Benchmark. I am Associate Professor of Software Engineering Department of Kharkiv National University of Radio Electronics. And my research interest is multimodal data analysis. Usually it's text, images, but my interest in merge this information. And I am member of Cost Action of European Commission multi-generation, multitask, multilingual and multimodal language generation. And it provides me a lot of sources and networking for my research interest. And at the same time, I'm coordinator of Tech Talents educational project in Kharkiv. We provide a lot of opportunity for students of Kharkiv University, and we provide him extra courses. And last year, we have courses computer vision and natural language processing. And final exam, we offer to contest on Canva. It was amazing event. It takes 11 days. Students from our educational project make about 200 submissions. And there was idea to separate natural language processing problems in other direction, and prepare a paper for this workshop. Objectives of our paper: create Ukrainian language dataset, critical problem of low resource language such as Ukraine is lack of unlabeled dataset for pre-training of word embedding or large data deep learning model, and the labeled dataset for benchmarking existing methods. And we need to improve quality of language, and we want to create this dataset. And the second part of our paper is benchmarked transformer models on created dataset. Each kind of sources for our dataset. We download news from famous Ukrainian news sites. It's 7 sites, and we try to download news for last couple years. It's about some less 100,000 text worth. And we should prepare data for dataset. First of all, we remove white space, we remove incorrect symbols. The next, we should to remove some information which can help which will be data leakage. For example, some news sites write this news. You can download this news from, and after that, source of the site. And we replace this text because it helps our students and our classifier to memorize site, not generalize this information. After that, we remove all duplicate of news. For example, daily publication about COVID statistic, about type of zone of different regions. All this information effect on memorize classifier, not generalize. After that, we clear on non-Ukrainian language pages. We remove English pages, pages on Russian language, because we want to compare our models only on Ukrainian text. And other data leakage is sure. And as a result, we have dataset which consists about 82,000 text. About 12,000 text will be removed from various reasons. And we split our dataset in train set 57,000 and test set 24,000 samplers. And all subsets and train and test have a similar variable distribution. And the interesting fact, we different safe title and text, and we compare word in title and very popular length of title 10 plus minus 1 words, and very popular length of news less 200 words, it's about 40%, and less 400 words, it's about 60%. And for our benchmarking, we should use magic. Our dataset classes are unbalanced. It's real, practice, and word. So we need to use metric which will be we use macro average F1 scroll matrix, which is resistive for unbalanced classes. And we should to choose models for our benchmarking. First of all, we choose multilingual BERT. It was uncased and BERT-based base model, not large base. And one moment of this model, multilingual BERT model trained on a huge amount of data, multilingual data. There are about 108 or 4 languages. It's usually Wikipedia data, but last benchmark, multilingual BERT made on some dataset without Ukrainian language. So we should continue that multilingual BERT train word embedding on Ukrainian dataset, but benchmarking model without Ukrainian language. It's some restriction for this model. Next, Slavic BERT. It's Mbert-based model, which trained on some Slavic corpora, but there are no Ukrainian corpus. So they probably, I guess that Slavic BERT should generate some Slavic morpheme or other idea, but Slavic BERT not adopted for Ukrainian language. The next model is Ukrainian Berta. It's Ukrainian Roberta. It's model trained on Ukrainian Wikipedia and Ukrainian Oscar part of Ukrainian Oscar dataset. The next model, Ukrainian Electra. We think that Electra model provides some better results compared with Roberta. Probably Ukrainian Electra will be the same compared with Roberta. And the last XML Roberta based model, it's a model which trained the same way as multilingual BERT, but it uses wedge architecture and it has more embedded layers. Okay, let's go. Pipeline of our experiment. We try to benchmarking our model on 2 parts of datasets. 10% of full datasets. It's a real situation in production when we don't have a lot of sources to train model on big dataset, or when we don't have a lot of sources for labeled big dataset. So we can try on a small part of full dataset, and we should understand what kind of result we have. And second experiment we make on full dataset. And we train our model on title, on full text. And we compare our model in the same train condition. The same number of training steps, the same computation time, and the same hyperparameters. And we have the next result. So we can see on this table 6 model, 5 transformer model, and first line is baseline TDF, ADF bag of words and SVM classifier. So classifier, and we will compare this baseline with our model. And we can see 4 columns, and there are different types, different part of dataset. First result, we can see that XML-R model provides the best result on a long test when we work with full text of news. And but we should to remember that this model is large and require more resources compared with other transformer models. The next result, UCR provide best performance for short text. So if we try to classify source of news only based on short text, on short part of that set, it provides better result. The next, we want to compare multilingual BERT and UCR. UCR provide each time better result compared with multilingual Roberta. 5% for short text and 36% for long text. And the next, we should compare UCR and UCR Electra. For short text, UCR provides better result, but for long text, UCR Electra provides better result. So we can see an area of for each of models, and we can see that Slavic BERT don't have significant performance compared with multilingual BERT, and Slavic BERT have the same result as multilingual BERT and don't have any opportunity for Ukrainian language if we want in future to use. And interesting result, simple baseline. It's linear SVM classifier based on bag of the word on long text, provide result not much worse compared with XML model, but we should to understand that SVM classifier require about 50 minutes to train. So the main results of the slide in future, if we need to make fast result and compare and make fast exploratory data analysis, we can use this approach. All this result we can see on this conclusion slide, reference on our conference and contest on problem. And thank you for your attention.
Thank you, Alexey, for the presentation. And it was, I like that you prepared this data set and published it for public use. Really great effort. So while we're waiting for the questions from the audience, oh yes, Alexey, but if you don't mind, I will jump in. So we have 3 Alexeys here in the conversation. So my question is about those results. So can you please jump back to the table with the main results? Yeah, this one. And I'm curious. So your main task is to classify the source of the news article. And
yes.
Have you tried to interpret how the model works? I mean, so you take the article text and whether there are any keywords that are crucial for the model to understand what are the source of this news article. For instance, you have this Ukrainska Pravda, right? And probably when you're dealing with the long text, because we see that the results for the longer text are much better than for the shorter text. So probably there could be some crucial keywords in the text that mark the specific source. For instance, somewhere in the text you see the mention of, for instance, the source, like Ukrainska Pravda or Новое Время, something like this. So have you tried to find out what are the main sources for the model of how they make such decisions?
Thank you for the question. I split your question into parts. First of all, interpretation of transformer model. It's very challenging problem, and it's very popular problem when our transformer makes a decision. We can try to which layers of transformer provide this information, and I work with this task. And I compare with other language. If we see how to transformer work with an English language, German, it works with whole words. For Ukrainian language, it works with parts of words. I don't know why it problem addressed to word embedding of transformer. So I tried to interpret how to transformer found decision, but it's I don't found significant result. Second part about stop words in news. This problem we start to solve when we try to find data leakage. And we create ADF matrix of bag of word, and we make He quadrat for different words, for different news, and we analyze the top 20 of these words. And if we see that these words provide information about news. For example, some news agency finished news details you can see download from this site. We all the sentence removed and replaced with sources. If we found some words, for example, some words which use after. For example, if he started description of images, I don't remember sentence of words, but we sometimes found this example. We left it. So maybe some features of authors. Yes, we sometimes see these features. So some news agency and some authors have some style, and this order of sentence can show what is the news.
Yeah, I see. So the authors also could be a significant feature. Thank you. And Alexey Ignatenko, so please go ahead.
Yeah, I have read in your paper that XLMR here, it has a significant computational advantage over other algorithms. So taking this into account, we can say that maybe Roberta is like have a significantly better performance, because if you can provide more resources, maybe it will outperform XLM.
Thank you for the question. Really, we compare some different types of model because the XLMR model required and 3 times more sources. The main idea to compare what price we pay for this significant result. So if we compare long text and large training set, we Ukroberta have result in one divided 100. So it's very small difference for large difference of model. Yes, you're right.
Thank you. So seems we don't have any other questions. Okay, so Lydia, please. Thank you.
Hello, thank you for presentation. And if I right understand, you're classifying news on some terms. I right understand? And which terms you use, and which keywords you use for determine them?
Lydia, thank you for the question. In our solution, I don't make any preparation of dataset before transformer. So I use full text or title for input to transformer, and transformer-based model yourself try to found keywords or key part of words to generalize it and make and classify text. So I don't do any preprocessing of data for classifier.
Okay, you don't have some terms. You just classify all text.
Yes,
on different clusters. Yes.
And 7 sources of news. And
so if I may, so they classify. Yeah, sorry, Oxy, please.
I would like to add that when I try to analyze word embedding of transformer, it don't use whole of words. It use part of words. So we cannot say about terms, about sequence of words, about bag of words. Transformer work in some different way.
Okay, thank you.
Thank you.
Yeah, so I just want to add, Lydia, that the goal of the paper was to classify based on the source of the paper, like news agency, not on the topic or any other means. Artem, please, do you have questions?
Yeah, thank you. Thank you, Oxy, for your interesting report and for your data set. And I'd like just to ask if your dataset contains original versions of documents or it's somehow changed.
Our datasets have original text with removing some parts of this text. For example, spaces or wrong symbols, or some information which is data leakage, which help to classify news with some wrong features.
Yeah, but why I'm asking because
Yes.
I was presented the previous presentation, and my model was trained on news exactly and on the news portal Ukrainska Pravda. So maybe we can utilize, if you say that this data set contains the original versions, we can even try to apply this model in order to build to project sentence representation into two-dimensional space in order to compare the retrieved clusters for Ukrainska Pravda, for other news article, and to reveal the dependency between sentences for each source. Maybe it will be useful later to for other tasks. As I understand, you may utilize your model for the faithfulness checking in order to understand whether this news portal provides true news or false news and so on. So thank you for the data set. I suppose that it will be really useful for the investigation and for me as well. Yes, thank you.
Thank you. It will be very good if you can use this data set for your task.
Yeah,
thank you.
So thank you, colleagues, for finding this opportunity to collaborate. At least we have one outcome, positive outcome from our workshop in terms of collaboration between different research groups. So probably, Artem, you can come next year with the results trained based on Alexei's group data set.
Yeah, of course.
Okay, thank you so much, dear colleagues. We run out of time. So let's conclude and finish our first Ukrainian Natural Language Processing workshop hosted by ICTERI conference. It was our pleasure to have you here to listen to your presentations. We have different kind of topics from different perspectives, and I believe that next year we will see you again with next steps in your research, or probably from totally different perspective. Also, we encourage others who listen to our workshop to submit your research and to join our community of researchers working on Ukrainian NLP domain. For me, it was a pleasure to have international representation here. We have researchers not only from Ukraine, but for instance, from Germany as well, and our keynote speaker from Ireland. So I think, and probably Alexei Ignatenko will also commit on that it was a good first success. As we said it in Ukrainian, not that glivki mlinets, right? So, I think, and I wish to all of us that next year we will have the whole day for our workshop loaded with interesting papers, and that will benefit for whole Ukrainian NLP community. Thank you again, and thank you, Vadim, for helping us to organize all this event, for supporting us through the whole process of preparation. Thank you so much.
Yeah, thank you.
Thank you for organization.
Thank you for organization.
Have a good one. Bye-bye.
Bye.
Bye.